video response from my man, but I would rather a written response, but changed it to a video response. So let's just jump in here a little bit. Let's look at, oops, gotta open it up. Let's look at Structural Concrete Building Code, ACI 318-11, commentary. 18.3.22.2.2. At crack sections, concrete resists no tension. All right, let's just use someone else, a little bit of triangulation, if you will, to get the point across. It's what people do. You know, psychology, how much I love it. So sometimes the messenger is the one that gets killed. So now you got to kill, not me, but you got to kill ACI 318-11. And surely, if that's your intent, you can work on killing it. Just attack the source if that's what you want, the source of their conclusion. But it resists no tension because it's already failed in tension, theoretically already failed in tension. Let's go to, and I'm going to get to this, crack inspections. So you guys remember I did this video some time ago, and these just screenshots. Grabbing some of my data I have that going back over it again. But if we look at the BPA, which now we know is a CEI, the inspecting engineer for the bridge. More importantly, the members showing these small cracks, that's their determination of them. Remember what cracks are a failure, right? Are truss members that share the same blisters at the canopy of the already stressed members. Number 2, stressed on 130.18, and number 11 stressed on 129.18. So it seems, grammatically backwards. The person puts the dates in reverse, but maybe they were thinking number 2 to the left, so this is how they work it in their brain. I like doing things chronologically. So number 11 was stressed first, guys, on the far right, was stressed first. Then number 2 was stressed. So don't get this confused. We believe this first stressing operation has temporarily created a tension on members number 3 and number 10. So we know number 11 and 10 are connected, and number 2 and 3 are connected at the nodes, thus creating cross-sectional cracks, transferring the tension loads on the steel in these members. No other stress members within span 1 show any cracks similar. See, remember similar? I talked about that. That's pretty witty of them to say similar. Doesn't mean it. To me, this implies that other cracks are present. Okay, so let's jump to. I've got to skip over one thing here. More of the report. And this is where we see the more of the report and how they change it to thousandths of an inch to hundredths of an inch, and it's quite playing with numbers here. And let's just scroll down to what I did roughly was, this was in my video of previous. Now, if your intent is to find me wrong on something, you should just troll this. You might find that I'm off by my location on some of this stuff. But, some trolls are intent to prove me wrong. Hey, all you're doing is correcting my mistakes. I appreciate it. So you maybe prove me wrong, but I just leave your comments there, and we can keep it as a correction or alteration to how this is done on the fly. So remember, this was post-tension first as per BPA statement on 129, just 2 months before, 1.5 months, 45 days approximately. No, it was the 10th. So about 40 days approximately before failure, this was tensioned. But what happens when you tension this? We see that when they tension this, put compression on this, so they tension the rod, putting compression on this guy here, it created with the BPA CEI identified as tension cracks on number 10, which we can use the conversely statement. So conversely, when I compress this, it puts this in tension, so it's stretching this, elongating this member here. So conversely, when I detension this, it now compresses this member here. So we can see that based on the CEI that using conversely, and you guys can listen to that again if I lost you, because I know how I talk sometimes, is that, so conversely, if you take tension off this will put more compression on this. If it's putting more compression on this, that means the forces are redirecting down 10, as I've always stated, and that's when they have to come out. They still have to resolve themselves onto the supports, and that would be left going through the deck, which would then be left going through the post-tensioning of the tendons. Now, a lot of people say it's just not, it wouldn't work. So, I might have said that, and I've said it before, and I don't like post-tensioning. You guys know I'm biased on that. But the but part, in theory, this should work. It's just a tight wire. It's just a very tight wire, and you can't make this collapse unless you can compress and you have to crack the deck so it can redirect and fall down. You also have to crack the canopy so it can redirect and fall down to the ground. But if you can't crack the deck or the canopy, the forces will always, like the books I try to describe to you guys, where you hold books in your hand, right? Grab a mess of books, put them between your hand, that trick there, press hard. As long as you're pressing, the books will not fall. So if you start releasing stresses, though, your hands, the books will fall. And this is why I say the post-tensioning and the tendons started failing. And to make them fail, theoretically, you wouldn't think it would be possible because of the amount of millions of pounds of force they're applying. But I think because they created a new moment that was not predicted by Denny Pate, or apparently maybe this is Erica that might be their post-tensioning expert. I'm throwing that out there. You guys control it and look for it. And she might be the post-tensioning. You guys got to look for that on your own, or maybe I'll give you a little hint towards it. But apparently Erica, and you know what, I can do that. I can give you a little hint to why I think possibly Erica might be the post-tensioning expert. Now, we can't throw her under the bridge, although a lot of people may like to, literally, because post-tensioning is just so theoretical that unless you've got a crazy mind such as myself that's always looking for different load paths, you're just going to believe what you're taught, and you're not going to be able to extrapolate differently. All right, so this is roughly where the cracks are, and I think I told you guys I'm not sure where they measured from, so I have to sort of guesstimate here. Was it here? Was it here? They don't actually tell their starting point. Let's do this. Let me bounce out. So, cracks report after shoring removal, February 28th. All right, this is February 28th. Remember, the tensioning was not done until the 29th. So they removed the formwork, the false works. So remember, and I don't know how much shoring they're talking about. Was it underside, or was it the shoring in the deck between the canopy and the bridge deck, or was it the shoring that was from the ground to the underside of the deck? This is ambiguous for me. Cracks inspection on truss members after formwork, scaffolding removal. See, I just don't know where this is. But we see it's beforehand. And so the structure under his dead load, this was just stupid. Why would you? Even I love experimenting, guys, and taking stuff to failure. I build stuff and then I just destroy it just for the sport of it, to see, knowing that it's going to fail the way I'm putting it under the loads, but I can't help it. Can't help myself. This is something I would not even have attempted to can't help myself with. It's 175 foot long. I don't know how much shoring, or all of it apparently, or that was removed or alluding to. Concrete just can't do this. So I don't get this part. This right here shows just ridiculous staging, or steps, if you will, scheduling. This is scheduling, is what a lot of people refer to it as. This is just ridiculous to me. You would think this would be done after some post-tensioning. Now, let me add that crack monitoring, we're going to jump on crack monitoring, and I lost where I have my crack monitoring images from loading up. There's somewhere in here. the crack monitoring from forever ago, May 14th. These are reloads, obviously, because I obviously did this a year ago, not May 14th. But the crack monitoring, yeah, obviously I didn't do this May 14th. It's a long time ago that we watched this. And these are the plates, etc. And that's the jacking tool, as you can see now. And it had to get down there. And that's number bottom of 11. That's the one they're working on, obviously. And that's the one that's sitting on top, which I think I've made a mistake a few times now. It's sitting on top of the pier, the other end of this, with the J-hook, by the J-hooks. And this one is still in the deck, the other end of this. Let me pause this and jump to something. Bear with me. I'll only hold this up a few more minutes. So I think it's noteworthy as I was searching for what I wanted to find. This again. Let's hit on this again. Look at this. Look at that. What's that about? 1.5 inches, 2 inches? You know, just guesstimating the thickness of this cover they put on top of here. So we're not looking at the structure. Apparently, maybe that jackhammering was just to remove this veneer coating they have up here. This weird coating, this weird veneer coating. This is not. This is 2 different pores here, guys. Okay, moving on. Maybe that's that reflective fancy stuff they were talking about. But I thought it was supposed to be added into the concrete. Nevertheless, you know, this needs to be addressed in the NTSB report, but of course they won't. Okay, so I had to throw this image in here, mostly for Embry. I like teasing Embry. He's got a hot rod, guys. You should see it. Embry, this is my, and everybody else. I do have a personal life still. I enjoy tons of anything. But right now I'm enjoying this 1980-something, so you can guess the rest of the year, GMC truck that I'm restoring. And I've already got many people trying to buy it already. And I'm like, darn it, I was so invested, conclusive file, to finishing it. Got a guy wanting to come out in the rain today to buy it, and he's told me he had a raincoat. He was quite triggered when I told him, hey, it's raining. I'm not bothering right now. So anyway, let me get back to the video. So back to the video. As you guys know, well, I guess you didn't know it delayed. I do, though. The state of Florida said that they were just a pass-through, if you remember, of money. Yet they had a structural engineer who reviewed the plans. In fact, his statement, I believe, or it might have been the other DOT Section 6, Group 6, whatever, who stated this, that they, not to be confused with their red inks, that they will put theirs in capital bold letters and red square boxes, or red boxes, if you will. And of course, that's the containing area. So this means the structural engineer these are comments here. Calculations performed using bearing plate dimensions different than those shown in plans. Engineer of record to verify that these bearing plate dimensions satisfy the design intent. So this engineer, the structural engineer, incidentally, for FDOT, those are theirs. Unless I stand corrected, those are his state. Sorry, I'm choking. So awesome. Here's I just noticed that this round call out in shop drawings, right? So 75. Right here again, more statement from FDOT, their structural engineer. These calculations are for 15-inch diameter spiral shown, and I think I mentioned in the previous video that I thought it was 13, and I said that they were calling 12, whatever, for 14-inch diameter spirals as well. So it's interesting, but here's the thing: the structural engineer is so ambiguous that he's not taking ownership of it. Yet he's still clearly sounding off. And I love his statement that he's saying the intent. So it's protecting him because, look, he clearly says, engineer record to verify that these bearing plate dimensions satisfy the design intent, which means the work structurally sound, right? So his choice of wording is awesome to protect him and FDOT. So I can't beat on that, but nevertheless, they're more than a pass-through if he's writing on the plans in bold letters and stating such. I think he became The FDOT had their regular engineer, if you will, their non-structural guy, reviewing this, and he passed it off to the structural guy for more questions and details and verification. And that's the response that we're looking at here. Such as, apparently, this is the response that we're looking at because they said they will do it in this format: squared, bold letters, capital, to differentiate against these. This is not FDOT. This apparently is FDOT. Elongation values shown are calculated by VSL and differ from plan sheet B-69. It's just a comment, right? So, awesome. And so you should have to address it. Here again. This is just showing in, just giving you more data. All right, guys. Let me get back and find this darn thing. Okay, I said I'd get you the couple of things here. Here we are. So we have Charles Tavella, professional engineer. He's for structural engineer also. And as we see here, to distinguish our notes placed on the shop drawings from the notes previously placed by the engineer of record, our notes were typed with all capital letters and the text boxes are squared. Okay, so there we have it. This is going to be June 27, 2017. Now, this is Bolton Perch asked, do you have any update regarding his submittal? As you know, it is critical. It is a critical element on the project and needs a review from Tallahassee. This is BPA, one of the BPA representatives, stating this to I believe this. Let me confirm it for you. This is going to be FDOT, I believe. Hold on. Yeah. So here it is, Alfredo Reno at dot state. And Alfredo Reno over here is a professional engineer, as I stated, working for the state, Florida Transportation. He then passes it off to the other state guy, the structural guy, at right here, sincerely Travis. Alfredo, please find attached to this email the release for construction as noted for the shop drawings for the post-tensioning deck, canopy, and truss for the FIU pedestrian bridge. Very clear what it's about. Right. Several comments added to the shop drawings require an engineer of record to verify some of the information shown, since it differs from the plans. For example, the dimensions of the post-tension rod bearing plates are different from the plans. If engineer of record has already verified that this information meets the intent of the design, then no changes are required. All right. So, for example, and I gave an example. Now we go to let me grab it for you guys. Jose Morales. Great. Pausing. So let's go right here. Erica Hango, FIG Bridge Engineers, has updated his/her response for the submittal. Now, this is Erica. If you guys recall, Erica is the one that changed some transverse post-tensioning in one of the accidental releases by FIU to the public. And I posted a video on that. Erica is what I'm alluding to, is probably their post-tension specialist for FIG Bridge Engineering. Incidentally, I no longer find her in the FIG's profiles. Neither do I find Danny Pate. But let's go on. Okay, I'm going to wrap the video up with this. This is a Barnett movement plan. And more importantly, it has the where they planned on putting the sensors. Now, you can look at this all you want and drive yourself crazy for whatever reason. It doesn't matter because the sensors went down, right? So the data is corrupt. You don't know what really was going on. But what's the greatest sensor on here? Well, they could have done a few things. They could have figured out the elongation of the tendons at this point without putting the caps on, move the structure, and check them again. If they became where they were no longer elastic, you could realize, oh, these cables yielded at this point. You got some serious issues going on. that they experienced forces beyond their abilities. So they could have checked that, but they probably assumed that, oh no, they'll stay elastic, and so if we go to check them, we'll get the same readings. No big deal, because they're going to rebound like a rubber band under that cycle, under that little bit of a cycle. So we don't have an issue with that. We can't check it that way, or perhaps they don't think that way. And then they said, okay, you know what? Let's go ahead and use sensors on the structure, and let's use this whatever this company is. Let's see if I can find their. Let me pause it. Give me a second. Let's use these sensors. We saw the sensors down here in one of the videos I showed. The sensors up here, but I'll show you another image before I close out this video, where it appears the sensors were here and approximately 10 feet apart, based on the measurements they offer. I'll show you that. Hopefully I will. Also, we see that the connection was at the curb. Of course, we also see it connected to the chains going from here to the transporters, but here it is to the curb, chain connected from deck curb to canopy next to lighting inserts. I showed you this too, and I said, well, this is craziness, because did they calculate that these chains are under tension? If they ever became lax, that means these things went upwards, right? So it would be awesome to have sensors, well, on the chains. Put them on the chains. They're going to be your most sensitive reading. But wait a minute. You're like, oh, well, that doesn't make sense. They're going to vibrate. Yeah, true. All right, you got to figure it out. But wait a minute. We have the best sensor of them all. Oh, I know what it is. It's all the cracks that we see everywhere. They're your sensors. All the cracks everywhere. Since they've exhibited forces, this is where you would put your sensors across all the cracks. That's the way I was taught, that if you want to know what's going on with cracks, you put crack sensors on them. You epoxy them, glass, etc. Imagine glass going across those things when you're transporting, if you epoxied on the other side of that, and the glass broke. Well, there you go. You now know that moved. So you have all these cracks. You could have epoxied glass across all of them. Just literally something low-tech as glass. Transported structure and the glass broke, you would know that you had movement there. Oh, but no, they use electronic sensors. And I have to say, nefariously, and I'll accept the one guy trolling me over there. Yeah, this is conspiratorial, but this is my background as far as, looking for things like this. So yeah, you can call it that way, that the sensors broke by accident. I'm using quotations in my hand. Now, they broke by accident. The sensors went down by accident. And yet these people got paid all that money still. I tell you what, if your sensors went down by accident, you're not getting paid by me. You're getting sued by me. I'm not going to pay you. You should have had insurance to protect us in this event, such as backup sensors, backup computers, backup systems. Unless, of course, you were on board with me wanting your sensors to go down. Wink, wink. Okay, guys, I'll end it with this image here. Of course, we've seen this image multiple times, but let's go ahead and look at it again. So this, I think I might have mistakenly called this bottom of number 11. It's the bottom of number 12. Number 11 is in the deck down below. This can't be the bottom of number 11. All right, these J-hooks, this is other data for you. It shows that they haven't been compressed, bent, they deformed. They look outstandingly awesome, like ready to install. We look at the back of this and we don't see these guys bent away, so we know that this bridge didn't slide away. It would have clearly bent these guys, deformed these guys, but yet they're standing proud, along with the, these are some heavy guys here, but they're standing proud also. Now, what are we looking at here? What's the bottom of this? Well, we can't quite tell, can we? We see that this is these grooves here where reinforcement or pipe sat inside of there. You try to match it up with the bottom of the diaphragm, and you sure enough should be able to match it up. We look at the embedment. We look at the plastic deformation here. We see none. No deformation on this rebar. We see this crack here. All this stuff will tell how it failed. We do see that something held on for a while right here, where it is pulled away from this track, apparently this rebar, and came in that direction. We also see that what did it was this moment right here, this bending point, was obviously embedded pretty tightly because we can still see surface cover of concrete on it. But now look at here. We now see measurements, and up here, maybe these are the where the sensors were located. So you can then go to those drawings. You find the distance of the sensors. You can now just start determining where the spalling took place. Aha! Here's this metal rod. Was this bent out of place before? You can now tell, if at all, if the bridge was during collapse, that it deflected at this point upwards. And it would be rubbing here. Not here, because if I were to grab rebar, it would probably loop. The bending moment would have been right about here with rebar. If you guys are any field people, you would know that you just can't grab it from here to bend it to get that. This would probably flex and not look so straight. It appears to be straight. Then we look at these stains. Okay, so now stains it's great, but there's also measurements, and plywood stains they look pretty square. Something is did a 90-degree here, so parallel. So this would be nice to be able to figure it out. Maybe that's 8 foot. I'm guessing 10 foot here. That's my guesstimate. Now looking up here, look at this. We've got a circle, a circle with a line through it. So we can only find out where that came from, where it came from. Here's that flex we looked at when the bridge pushes away and pushes back. I find this the most interesting of all. How the cabling was able to pull it back in place, that it's not totally trashed up here. This is what I find the most amazing. Perhaps it's just pixelating in the video we watch, but right here, this is where the chain is hooked to at the end there. These are the chains where they're hooked, obviously bolted to the ceiling. Then we've got some writing up here. I thought this was STE. It might now be 5TE. And we now have so much, same thing here. So this appears to be grinded off. They ground off the sensors if they were on this side of the structure. Let's go ahead and scroll down there again, give you another dab at that. See the way that looks? And see the way this looks? And we're in line with each other. Perhaps they use a plumb line because we don't see a 4-foot level, if you will, a typical 4-foot level that would trace that down to there. So perhaps they use a plumb line, or they didn't need it for these sensors. I don't know. But now we're looking at their sensors, where they place them. Apparently where they place their sensors. But what's the best sensors? All these cracks that were already existing, those are the best sensors. They could have put literally just glass across them to check for structure, for movement. These high-tech sensors obviously failed, and that I find amazing. This cable whip has always got me fascinated. I've seen it blowing in the wind in a video once, and I find this, whatever this is, just to be interesting. I'm terminating video. I've got to go. I've got to get back to work. Sorry, I'd love to give you more, but that's where we are.